Hey everybody. Today we're doing some examples using the comparison tests. Here are the three that we're going to do. Right off the bat, let's recognize that there's more than one way to do each one of these. My solutions aren't unique. Problem 1. Sum n equals 1 to infinity, 1 over n to the n. The denominator here, n to the n, is growing very fast. It gets big extremely rapidly. So 1 over n to the n is going towards 0 very rapidly. My instinct is that this series is going to converge, and I just need to find something to compare 1 over n to the n to, find some convergent series to compare it to. There's two important series to remember when you're doing comparison tests. The first one is the p series, sum of 1 over n to the p, which converges for p greater than 1. And the other one is the geometric series, sum of r to the n, which converges when r is between -1 and 1. So here we can tinker around with either one of those and stumble across eventually this comparison. 1 over n to the n less than or equal to 1 over n squared. So when n is 1, both sides of this are 1, so that inequality holds, 1 less than or equal to 1. And then when n is greater than or equal to 2, on each of these denominators I have the same base, the n, and then the exponent is larger on the left. So the fraction on the left is going to be smaller. So this inequality holds for all n greater than or equal to 1. The series sum of 1 over n squared converges, and therefore by the comparison test, so does the sum of 1 over n to the n. There's lots of other comparisons we could have done. Here's one other that would have worked, comparing it to the convergent geometric series, 1 over 2 to the n. Problem 2. Sum n equals 1 to infinity, e to the 1 over n. So I immediately see the 1 over n inside the summation, and I think about the harmonic series, which is one of the most important divergent series that we know. So I just want to think about e to the 1 over n for a second. So that can also be written as the nth root of e. Let's remember that e is about 2.72. It's bigger than 1. So no matter what root I take of it, whatever positive root I take of it, I'm always getting something bigger than 1. Therefore, e to the 1 over n is greater than 1 over n. Since the sum of e to the 1 over n is going to be greater than the sum of 1 over n, we know that the series in question diverges, because the sum of 1 over n diverges. Problem 3. Sum n equals 2 to infinity, 2 over n square root n minus 1. The series here is starting at n equals 2, so that I don't have to worry about dividing by 0 when n is 1. So I expect this one to behave like 1 over n to the 3/2. Just kind of ignore that -1 for a second, only look at the powers of n square root of n. So that's a convergent p series. There p is 3/2, which is greater than 1. A direct comparison doesn't help us, because the -1 in the denominator actually makes the whole fraction larger. And having a series that is greater than a convergent series tells us nothing. Instead, we want to use a limit comparison test. Let's do a limit comparison test for our series, which has general term 2 over n squared n minus 1, with this convergent p series we've just been talking about, 1 over n to the 3/2. I take the ratio of those two, put a limit as n goes to infinity, simplify a tiny bit, dividing by multiplying by a reciprocal, and then evaluate the limit. You could use different techniques here. I'm going to factor the highest power term out of the top and bottom. Those n to the 3/2 cancel, and now when n goes to infinity, I just get 2. Since that's a finite number greater than 0 but less than infinity, the series sum 1 over n to the 3/2 and sum 2 over n square root n minus 1 both converge or both diverge. Since the sum of 1 over n to the 3/2 converges, so does our series.